Welcome back, ladies and gentlemen. We're going to be continuing right now with more ionic bonding. You've already been covering the basics. We reviewed ions, we reviewed binary atomic compounds, the simple ones, right, that involve one metal, one non-metal. But then I mentioned at the end of last video that there's going to be something new, polyatomics. Now, polyatomics are discussed on page 11 of your booklet. And polyatomics are actually exactly what they say. The word polyatomic is actually two words. Well, okay, not two words, but one word and a prefix, a thing in front to change what the word means. Atomic here, of course, means atoms, or we'll just call them things for our purposes right now, and you will see why in just a second, because poly means many. Polyatomic ions is the usual full phrase, which means that if I put all this together, this is the many atom ions. That's it. That's all it means. It means that there are many atoms to make a single ion. And that's it. Otherwise, everything about it behaves exactly the same as all the stuff we've already learned and reviewed about ionic bonding. The only thing you need to keep track of is the fact that polyatomics will be more complicated. Now, in order for us to work with polyatomics, what you guys are going to need is your copy of the periodic table, because the first page is a convenient periodic table. The second page we're not going to use quite yet, but the third page, this area here, these are polyatomic ions. And I don't expect you to have everything about the polyatomic ions memorized because they're pretty weird. They don't behave in a predictable way, unlike the binary atoms that we talked about last time. So instead, I would like you guys just simply to have this handy so you can look stuff up. And that's it. I don't expect anything else from you. Even on a test, I would give you this. So let's take a look at some of the examples here. The first one we have is we're going to do from formula to name, just like last time. So the example is KNO3. Now, that's a good indication that it's a polyatomic. You see how it's got more than two elements, right? Previously, we did stuff like NaCl. There's sodium and there's chloride. Two elements, very straightforward. Now, we've got three, K, N, and O. K being potassium, N being nitrogen, O being oxygen. Potassium is another one that uses the old Latin name. I'm trying to remember what it was. Chytrium, maybe? I'd have to look that one up. I don't know potassium and I don't know sodium. I don't know why. So, there's three atoms here. So, it is a many-atom ion, or a many-thing ion, whatever. So, how are we going to name this? Well, much like before, we start off with the metal. The metal here is, of course, the first thing listed. It is potassium. So this becomes potassium. Then we have NO3. Now, if you're not paying attention, you would try to name this as nitrogen oxide or something weird like that. You know you've messed up when you've got too many words. All of the polyatomics, all of the ions should only ever be two words. So if you see this, you've done something wrong. Instead, you got to look up NO3, and you got to look it up on your periodic table. And the periodic table is in alphabetical order. So, or this chart is. So N, whatever that thing is, probably starts with an N. So I look down the list down here, and I find it. Oh, there it is, N. Now you got to be careful because there are multiple that look kind of similar. This is NO3, which is the first one on that list, not the second one. The second one is NO2. So we want NO3. And it says here that is called nitrate. So it becomes potassium nitrate. And we're done. That's it. All we had to do was know to look it up and then write it down properly after we cross-reference, read it to make sure it matches. And that's it. That's all we need to do. It's very straightforward, very simple. The only real problem, as it were. The only real hiccup is one of the unusual ones. Because when you look at this chart, I will usually tell students, okay, look at this chart. There is one positive polyatomic ion. Most of them are negative. Can you find it? And the students will sit there and they'll look and they'll be going, well, I don't see any positive ones, and that's because the positive one is up there. It's hidden out of the way of all the rest because it's different. The positive one is ammonium, and ammonium would look something like this. So that's ammonium. So if you had something like this, it'd be very easy for someone to go, oh, what do I do? Well, it's still the same. You see multiple atoms together. Remember the definition, multiple atom ion. You see multiple atoms together, so you just simply take that, cross-reference. This, I just said, is ammonium. And this one, of course, we just looked up. This one is nitrate. Ammonium nitrate. There you go. That's it. That's usually the most complicated one, is when you get two polyatomics like that. But it's not so bad. You just have to know to look it up and keep it very simple. So once you've looked it up, once you've seen this information, you've written it down. Done. Well, there's another example. Let's take a look. Maybe there's going to be a fast one. Maybe there's going to be something sort of a trick. Nah, not really. Well, a little bit. The last one here, we'll put it over here. The last one here talks about something in brackets. And brackets always confuse people. We just have to remember what brackets means. Now, if you guys remember the discussion we had when you guys were in class, brackets talk about how different elements are bonded together. So the example here from your book is ZnCl, where is it? O3 bracket 2. Now, a refresher, because, couldn't hurt to review. The brackets are telling you that there are multiple of everything inside the brackets, right? There are a couple ways we could do brackets. We could do 2ClO3 like this, or we could do ClO3 bracket 2. The two things mean something different. This means that there are two of these, but they're separate from each other. So like one of them is here, and the other one is there. And they're just off in space. One's over here, one's over there. This, with the 2 as a subscript, means that in some way they are connected. They're, duplicates, but they're connected. So that would be the same as me doing, say, that, connecting them together. Now, obviously in our real one, there's also a Zn in there. So if I want to throw that guy in there, probably look something like this. And that's about right. And you can probably see why we put ClO3 with a 2, because there's two of them, and they're just attached from either side, and they're identical, so why would I bother doing each one twice? And I can just write it once. I mean, yes, maybe writing Zn ClO3 is correct. I mean, it's accurate, but it's messy and it's hard to understand. So we don't do that. But it gives the same piece of information. So anyway, that's what the 2 means as a reminder. How do we write the name? Well, surely it must be much more complicated because there's these brackets, and I just had to spend all this tangent discussing how brackets work. Yeah, no, actually, it's just the same. It's still zinc, because that's what Zn is. We can find that by looking it up. And then we just have to write down what this is. Well, it's Cl, so we once again, multiple atoms, so we check our chart, and we find it ClO3 right there. It says chlorate. Well, okay. Chlorate. Done. That's it. We don't need anything else. Anything to do with polyatomics, it's really quite simple. The hard part is just recognizing what it is and knowing what to do. By itself, the individual steps are very straightforward. You just look it up, write it down. Okay, well, that's for formulas to names. What about names to formulas? Things must be a little bit trickier. It was last time we did stuff. This time, yeah, much the same. It's going to be a little bit trickier, but not a ton. It is not going to be too bad because when it came to binary atoms, chemists kind of expect that you have ideas memorized, that you know the pattern in the periodic table, right? The pattern, again, just as a reminder, is this idea that the table, real quick table here, that's almost right. There we go. That the pattern in the table comes down to the way in which the charges are laid out. And we talked about the fact that this one here is going to be 1 plus, 2 plus, 3 plus. And then these ones were going to be 1 minus, 2 minus, 3 minus. And then, of course, right in the middle, you get your 4 plus and or minus, because it can go either direction. That's the guy right in the middle. That's good old carbon. So for binaries, we assume you know that. Whether or not you do, of course, will depend on how much practice. But for polyatomics, we don't. That's one of the reasons I don't demand or expect you guys to memorize it, and instead we give you a list. Because there's so many things on here, and they're all weird, and they don't seem to follow any particular pattern, so it's a little bit mean to make you memorize them all. So we're not going to. So if you guys take a look at page 12 here, we've got some examples of how to do this. The example we've got... Oh, no. Sorry. Page 12 has got more examples of working through the formulas to names. We're going to do it the other way. So page 13 has got formula to name. So it says here we've got lithium sulfate. Okay, so there's our example. Lithium sulfate. Well, we have to put it together. So lithium, we look that one up. It's a metal. We know it's a metal because it's first. And the first metal means it's going to be somewhere on this side of the table in the positive areas. So lithium, we look it up and we get the element Li. Okay, that's pretty straightforward. And then we look up sulfate. Now, sulfate we have to check by looking here. And we look for S, we look for sulfate, and we see it right here. And you'll notice that sulfate on your table is actually spelled two different ways. There's sulfate, like I wrote there, and there's also this one. They're both the same. F version of sulfate, that's what the Americans use. Brits and Canadians tend to use the PH version because we like extra letters, I guess. Either one's fine. I don't care which one you use. Either way, we look it up and we see sulfate has SO4. And there it is. Now, unfortunately, we can't just leave it like that because we have to remember that ions always want to be balanced. So they have to balance. But in order to know if they're balanced, we have to check their charges. So we get out our information. We get out our colors here because I do like some extra colors. The lithium's easy because lithium is about here or so on the table. So that's in the 1 plus category. So we know what lithium is. Lithium is always going to be 1 plus. But what about sulfate? Now, if someone's not paying attention, they might try to look it up, and they might be like, okay, well, sulfur and oxygen, where are those on the table? They're about here in the oxygen area, under 2 minus, but I don't know, does that really make sense? How would I put all that together? I don't really know. Yeah, you don't have to do that. All you have to do is that when you look it up on the table, it tells you what the charge is. You just look there. So, for example, sulfate, it says right on here is 2 minus. So I just put, this is 2 minus. Done. Well, okay, almost done. We know what the charges are now. We didn't have to memorize sulfate, but we need to balance. Now remember, we discussed last time, there's a few different ways to balance, but the easiest one is probably just to make sure that the two sides are the same. This one is 2 minus. This one here is 1 plus. So that means I need 2 of these guys to equal one of those guys. Right? Because this guy's worth $2 and this guy's worth $1. Well, I got to make them the same. So I'm going to need an extra one. If I were to draw it, I would do it like this. Right? These two combined become 2 plus. These two combined become 2 minus. That's it. Very straightforward. Okay. Now, how do we name it? Or how do we write it, I should say? Because we already started with a name. Well, I put it all together. Li SO4 with a 2 subscript. Reminder, as we just talked about, subscript is how you know they're connected. If I were to draw this, it would probably look something like Li, SO4, Li, and some sort of connection like that in some way. Okay? So we've got another example. We'll do that one. Hopefully this is all coming together nicely. The next one is magnesium nitrate. Okay, magnesium. That's about there, I think. It's in the 2+ category. So we got Mg, it's 2+, and then we look up nitrate. Nitrate, we of course check here. The way you can tell is because it's got an 8 ending. Well, I should say it's not an IDE ending. IDE generally means it's using the table. ATE, not so much. So this is going to become NO3. We have to look that up to know, unless you happen to remember from the last time we did it. And if you check there, it says NO3 is 1-. That's it. That's all we need to know. Well, almost. I mean, we have to actually balance it, right? Just like we did over there. So in this case, this one is worth 2, and this one is worth 1. So that means we need 2 of these guys. Again, I could draw it out and say, okay, NO3 with a charge of 1-, and we would go with Mg NO3, and there are 2 of them, so brackets 2. Make sure you put the brackets, because Mg NO3 bracket 2 is very different from Mg NO3 2. Quite a bit different. 32 is not the same as 2 times everything in the bracket. All right, that's how you write that. It's pretty straightforward, I hope. I hope you guys have no problem with that. If you guys take a look, there's tons of practice dealing with this on page 14, so you guys can give that a shot. All right? A nice short one today. I'll leave you guys to it. See you next time.